All right, welcome to Calculus, what is this, BC? Today's the 29th, almost done with January. We're talking about improper integrals, and today we will talk about, this looks upside down to me.
It is. You wrote it upside down, like, oh, there you go.
Gabriel's horn.
Okay. Queen. Three.
That's bizarre. Alrighty. We are on improper integrals, correct?
Does your computer have to be facing your face?
I suppose if they want to see me.
I don't want to see you.
Okay. Right now I'm not taking any responses because that's just way too hard to concentrate on. So this is going to be, you can, and by the way, put your phones away. You weren't here, so you're safe. Nice hat, by the way.
Thank you.
My wife's, is that purple? What color would you use to describe that?
It kind of goes with my shoes.
Yeah, and your shirt.
And your personality.
So what is today's theme, by the way?
Workout. Muscle.
Workout? Okay.
Muscle Monday. So what was the thing about the phones that I missed? You said you weren't here.
Oh, some people in this class
Just at me, like.
were dissing me and said the number 3 sucks. That was the comment I got on the chat part.
Good.
And I was extremely hurt.
You commented on his video while you were in here?
Oh, for sure, yeah. What?
Those pants.
These are Luke's. He spilled pork juice on my pants once, and I needed new ones, so I'm wearing his pants because I haven't given them back.
I love how they're. You ready for the flood, Flora?
No, I'm wearing fluffy socks, so like this is one
Yeah.
of the worst outfits.
You know,
I've
this
ever
this is a typical class where we talk about attire as opposed to mathematics.
worn. Yeah,
You started
your
it.
ball
Yeah, I know.
was
I'm the one
nice
that
today.
brought it up. I'm sorry. So this is what this graph looks like.
Where are we?
We are in number 7. And this is a little bit different because we're going to go to a constant rather than infinity. And what you're not allowed to is to put 0 in here. So you're over here at, you're figuring out the area between 0 and 4. But you can't get to 0. Right? Because you can't divide by 0. So we're going to take a look at how we're going to do that. And we're going to end up using the limit also on this. But I can approach 0 from what direction? The what?
Or right to left.
Right. So I'm approaching it from the right. So what it looks like is I'm going to take the limit as a, and the reason I chose a is because a is usually what we call this lower bound, as approaches 0 from the right. And it's going to be the integral from a to 4 of x to the negative 2 power dx. And so if you want, you can skip this part, but you do want to keep the limit, and you do want to have the proper antiderivative, which is negative 1 over x. And are we okay with that antiderivative?
Yes.
Right? And you'll see me just make this assumption now that I'm not going to have to sit there and show you that I'm going to add and multiply by the reciprocal every time. Okay. So now I'm going to have the limit as a approaches 0 from the right of negative 1/4 minus a negative 1 over a. And why does that look strange to me? Well, let's just see what happens here. So I'm going to get this. The limit as a approaches 0 from the right, negative 1/4 plus 1 over a. And a is approaching 0 from the right. So what kind of numbers are we looking at as we approach 0 from the right? Positive. What else?
Small decimals.
They're small decimals, right? Like,
Wouldn't they be bigger
what would be bigger?
than?
So a is getting really tiny. It's positive, right? So I'm dividing by really tiny numbers.
So it's going to be really big.
So this reciprocal is going to be really big. So where is this headed towards? Infinity, right? Because I'm going to have 1 over 1/10, 1 over 100th, 1 over 1,000th, and the reciprocals of those are 10, 100, and 1,000. So it's getting very large. So this is not going to have a numerical limit, is it? So the answer is this is diverges. Same type of problem here. So I'm going to have the limit as a approaches 0 from the right. And I'm going to have, what would be the antiderivative of this? See if you figure it out in your head. 2.
No.
2 is right, yeah. Because it's a negative 1/2, correct?
Yeah.
You're going to add 1,
Square root.
square root of x, right? And everybody sees where the 2 comes from?
Yeah.
Okay? And you're going to integrate that from a to 4. And so I'm going to have the limit as a approaches 0 from the right. I'm going to have 4 minus the square root, or 2 times the square root of a. So what happens there? Now again, our numbers are going to get really small. They're going to be positive, but eventually they'll be like 0.000001, right?
So we want to get close to 4.
It'd be close to 4. So this one converges to 4.
So then how do you find the area under them?
That is what the area is. That limit.
Okay.
Okay? That's what that area is.
Yep.
All right. Alrighty. So on this one, I'm going to have the limit. Am I choosing A or B? Why did you choose A?
That's what we're doing for the other one.
Okay. What about in this case? Why did I choose A here? Well, if I look at this, here's 0. Right, Jaden? And here's my, correct?
Oh.
And here's 0, and here's this. Are you going to choose A in this case?
No.
No, we're going to choose
B.
B. And what's it going to approach? What can't it be?
1.
1. And where's it approaching it? From the right or the left?
Left.
The left. So you're looking at values like 0.9, 0.99, and so on. So I have, ooh, I bet you we forgot what this is. The antiderivative to this?
Oh.
Parentheses that.
It's got a square root.
It's something trig related.
What? Yes, it is trig
Oh
related.
boy.
Oh,
A is equal to what?
1.
1.
Oh, we're gonna have to.
G of x is equal to what? X.
boy.
Square root
What is this?
x is going to equal what? 1 times,
X.
no, what trig ratio? Sine. How can we check? Here's my triangle, here's theta. If I say this and I set up my ratio, what goes where? X goes where? Opposite. Where does the 1 go? On the what?
Hypotenuse.
On the hypotenuse. Opposite over hypotenuse. What's right here?
Square root of 1 minus x squared.
Is that what I have?
Yes.
So I pick the appropriate one. So now I'm going to have in here, and I got to figure out what dx is. So what is dx?
Cosine.
Cosine of
Theta.
theta d theta. So what I do is I figure out the antiderivative, And so I'm going to have 1 over the square root of 1 minus sine squared theta times cosine theta d theta. Which is what? Cosine theta over, what's this going to be? This could be,
Cosine squared theta.
right, but you're going to take the square root of it.
So just
Cosine
So it's just
theta.
just equals theta.
Which is what?
theta.
Theta.
D theta.
And then what is theta equal to?
The inverse sine of x.
Why don't you just put 1?
Because the sine of theta equals x, correct?
Well, it's just like.
So if I want to know what theta is, it's going to be the sine inverse of that ratio.
Couldn't you have just done that from there?
Yeah, well,
Could I have done what from where?
Make it sine inverse of x from that.
If I could I have gone there directly?
I'm so confused right now.
Okay, I don't understand your
I
question.
don't either.
Okay. I'm saying I didn't know what the antiderivative of that was, but since it was square root, and since we had just done trig substitution, I used trig substitution to figure out what it is. And so this is, we end up getting theta, correct, when we do our trig substitution. And I know that the sine of x, excuse me, the sine of theta equals x. So that must mean the sine inverse of x is equal to theta. So that means I'm going to have the sine inverse of x, and it's going to be from 0 to b. So I got the limit as I'm approaching 1 from the left of the sine of b, excuse me, sine inverse of b minus the sine inverse of 0. Remember, these are angle measurements. The sine of what gives you 0?
It's 1, 0.
Just gives all.
Okay? Now, I can plug 1 into sine, can't I? The sine of what is 1?
1.
5 over 2.
I mean, 5 over 2.
So my answer is pi over 2.
Wait, so why can't you, if b is going to 1, but you don't put 1 in as b?
I can put 1 in. You can remember how when we have a limit, let's say we have that, okay? I can't put 1 in there, correct? But I can come up with a function that is exactly the same as this function in which I'm allowed to substitute 1 into. That function in this case, in this particular one, is x plus 1.
Okay.
So the limit of this is 2.
Yep.
Because that value exists here, it doesn't exist here, but it approaches 2 on this function.
So you
Okay.
just skipped that second part?
So what I did here is I came up with an equivalent function. I cannot put 1 in this function, but I can put 1 in this function, and they're equivalent functions at every single value except 1. But I can use this to know what it is approaching here.
Okay.
And what is it approaching? It's approaching pi over 2.
Got it.
Okay? It's just that it's not as clean when you can simplify. Simplifying is a nice, clean, algebraic way. This is a trig substitution way, but the idea is the same. You're finding almost equivalent functions. Okay? All right, now, again, we're going to have the limit. We've done this antiderivative enough. We should know that the antiderivative of the ln of x is x ln of x minus x. We've done that a couple of times, right?
Yep.
Okay, so is it going to be A or B that we're going to choose the limit on? What aren't you allowed to substitute in here?
0.
0. So it's going to be A is approaching 0 from what direction?
Right.
Right. And so I'm going to have x ln of x minus x. Are you guys okay that we've done this a couple of times that I can just say, hey, we've done that? And I'm going to have A here, I'm going to have 1 here. So I got 1 ln of 1 minus 1 minus A ln of A minus A as A approaches 0 from the right. So ln of 1 is what? 0. So I get a negative 1 here. Minus what's happening here? Well, this is headed to 0, correct?
Right.
Okay. And this is headed, I don't know where this is headed. What?
0.
This will be a small number.
Or that'd be
Oh.
well, 1.
We're not sure, are we? Because this would be, if I put, can I put 0? I can't put 0 into here, can I? Correct?
Correct.
Right? And so I could have, I don't know what I would have here.
Couldn't you?
Like 0.1. What if A was 0.1?
Yeah, what if A is 0.1?
Well, wouldn't you just get continually smaller?
What does, that's what natural log looks like. So as I head to 0 from the right, where is this headed?
Negative infinity.
Negative infinity.
But then wouldn't you need to
So what is this? What's the answer to this?
diverges?
It's diverges.
No, I'm talking about control.
Do you have to put down that it equals infinity? Or no?
All right, what about this one? I'm going to break it up a little bit. I brought this back as a review. How would you figure out the antiderivative to this one? You could. You could. I would use substitution. Oh, what did you say the answer was?
Said it looks like the natural log.
That's exactly what it is. The natural log of the natural log. Okay, now, let's say you didn't see that. So I'm going to let u equal the natural log of x.
I already did it in her brain.
So yeah, that happens. Du dx is equal to what? 1 over x. So du is equal to 1 over x dx, which is right there, correct? So I can really look at that as integrating u to the negative 1 du, or 1 over u du. What is that? That's the natural log of u. But what is u? U is the natural log of x. Did you hurt your arm?
it in her shirt.
Oh, you stuck it in your shirt. Okay.
Yeah, she just lost
Okay.
her arm.
So, I'm taking the limit. A or B?
B.
B.
So you can't plug a 2 in here?
Wait, I mean A.
I knew it.
From what direction? Oh, A is approaching 1 from the right. And it's going to be the ln of the ln of x. So I have the ln of the ln of 2, whatever that is, minus the ln the ln of A. So, what is the ln of 1?
0.
0, correct?
Correct.
And so, but I can't take the ln of 0, can I? Right?
You just can't.
Okay, so e to what power is 0?
1. No.
Okay, yeah, I get it.
You see what I'm saying? And if you look at the graph looks like this. So this, where is this headed? As A approaches 1, where is this headed? Negative infinity.
So it's just infinity.
Yeah, so it's going to be infinity, so it does what?
Whatever it is.
Wait, why is A approaches 1 would it?
Because I can substitute 1 into here, correct?
Yeah.
And when I substitute 1 in here, I get 0, because the ln of 1 is 0.
Right. Okay.
Okay? So you're getting closer. What's really happening is you're getting closer to here, and you're headed towards negative infinity. All right, what about this one? In other words, I have this. E to the square root of x, and I have 1 over the square root of x dx. What do you think you should do? If you're not sure, the first thing I would do is substitution. What would I let u be?
Why do you have that?
Square root of x. So what's du dx equal to? 1 over...
Can we draw a line dividing this question and the last
Yeah,
question?
yeah.
So I'm very confused.
Now you're good.
How about a cleaner sheet? So I'll let u equal the square root of x. So du dx is equal to 1 over 2 square root of x. Would you agree with that? So 2 du is equal to 1 over the square root of x dx. So now this is going to become e to the u. Here's my 2. Here's my du. Are we all right with that substitution? Here's 2 du. Here's 2 du. What was that? That was this part right there. So what's the antiderivative of e to the u? E to the u. So I have 2 e to the u. So I have 2 e to the square root of x. I'm going to take the limit. Is it a or is it b? A headed towards what? 0 from the the what? Right. And I'm integrating from a to 4. So I have 2e square root of 4 minus 2e to the square root of 0. What does that give me? Well, because, or a, I should say, right? And I'm taking the limit of that, and a is headed to 0, and so I can write that can I put 0 into here?
Yeah.
Yeah. What do I get? 2 what? E to the second power minus 2. So that's the area it converges. Okay. Alrighty. So here's this equation. This right here is the equation of 1 over x, and you can see it makes kind of a horn. This is the surface area formula. All right. So I tried to compute the area of the surface area. And we did a problem like this. X 1 over t dt. And this would be the ln of x minus the ln of 1. Would you agree? Right? Because the antiderivative of 1 over t is the ln of t. Or maybe I should write it like this. The ln of t evaluated from 1 to x.
Why is it t?
Because this variable cannot match that variable. Because x is going to infinity. Or I can write it like this. The limit as b goes to infinity of 1 over x dx. Maybe you'd rather have it this way. And that's the limit, natural log of x evaluated from 1 to b. And I get the natural log of b minus the natural log of 1. You remembering this? This is one of the very first ones I did.
Are you just repeating it?
Yeah, I'm just repeating it. What do you get here? It what? What's your answer?
Infinity.
It's infinity, correct? Because the graph of this looks like this, and it keeps growing very slowly as it goes to infinity, right? So this diverges. Okay. Now, the reason I bring that up is if f of x equals 1 over x, what's f prime of x equal to? Negative 1 over x squared, correct? So, if I would substitute this in to figure out the surface area, I'd have 2 pi from 1 to infinity of 1 over x times the square root of 1 plus 1 over x to the 4th dx. Would you agree? All right. Now, this correct? Because that's what I just showed, right? So my question is, what about this function? Isn't that always greater than 1 by a little bit? Would you agree? Okay, so could I say that g of x is bigger than f of x? And f of x, this is f of x right here. So I'm multiplying it by this, this right here. I can't say that. I want to say this. G of x times f of x has to be greater than f of x. Would you agree with that? Okay, since this diverges, what has to be true about this? So if you think about it, here's the graph 1 over x. And its area from 1 to infinity goes to infinity. It has an uncountable area. Okay? Now I have a graph 1 over x times the square root of 1 plus 1 over x to the fourth. And it's bigger by a little bit. Okay, by a little bit. What can you say about its area? It must also what? Go to where? Right, because it just has more area added to it, correct? So it is also divergent. So in other words, this right here has to be divergent. So this process that I'm comparing two functions is a process when we get to series we're going to go more in depth with, and you'll learn it better than me just the way I'm talking about it right now. So what I did is I went through and actually did the calculus to show that it was divergent. And you're not going to have to replicate that at all, but I want to show you what it looks like. So that's where I started, right here. I rewrote it so it looked like this. And what I did is I wrote a little note. It says, look for the antiderivative, then integrate to infinity. Okay, I had to figure out what the antiderivative was. And so what I did is I have this, and then I wrote it, I took the square root of x to the fourth, and that's x squared. And there's the 1 over x. So I wrote it like this. Does that make sense where the x cubed is? And I let u be equal to x squared. So du equals 2x dx. And du equals, or dx equals du over 2x. And now it became this, which then became that. And the 1/2 canceled out with a 2 pi, and I was left with pi, and I had this. Okay? Now, I did integration by parts. And when I did integration by parts, I ended up with this. So then I had to do trig substitution. And I ended up with that. And then I had to go back, and I went to my right triangle to figure out what those were, and I came up with this. And then I had to go back and figure out, okay, what was u? So I came up that this is the same as this, which was the same as this, which was the same as this, and then I integrated to infinity and found out, oh, it diverges. And I thought, you know what? Doing the comparison test, comparing to a function that I could say, hey, this function is bigger than a divergent function, and since it's bigger, it's going to have more area than something that's uncountable, so it has to be uncountable, is a lot easier than doing all this work. Because this took me a while.
I can see
Yeah, I
why.
bet.
Yeah,
How much sleep did
okay.
you get last night, Gabriel?
So it wasn't a lot of fun. It was just a lot of stubbornness, and I was happy when I was done. Okay?
How much did you sleep last night?
I got this done like my wife was ill, so I got up early in the morning, and I worked on it from 5 a.m. to 8 p.m.
Did you lock earlier?
No, I didn't. I've been waiting for somebody to show up again.
Did she miss me?
Yeah, she does. She wags her tail every morning. Okay, so there is no surface area. In other words, it's impossible to paint, right? Because painting is surface. Now I'm going to compute the volume. This is the formula of the bottom. If there's no hole, which this doesn't have a hole, does it?
I suppose.
Okay, so what I did is I went from pi, I went from 1 to infinity, and I went 1 over x squared dx, which is equal to pi 1 over x squared dx, and that gives me the limit as b goes to infinity of a negative 1 over x from 1 to infinity, which is the limit as b goes to infinity. And I've got a pi here. I forgot to multiply through by pi. So I'm going to have a negative pi over b minus a negative pi over 1. And this is going to infinity. So now I got the limit as b goes to infinity of a negative pi over b plus pi. What does that head towards? Pi. So this converges to pi, which means it has a volume of 3 pi units, correct?
But no surface area.
But no surface area. So I could fill it with about approximately 3.14 gallons of paint. But those 3.14 gallons of paint can't paint the outside or the inside of it.
But like it.
Hence, there's a paradox. It's called Gabriel's horn. Which I think is kind of cool. Okay? And what I like is I like the topic of topology. I like the topic of Mobius strips. I like the topic of Klein bottles. I like these ideas that there's no inside or outside and these ideas of paradoxes. But you can't get there till you get it to a higher level of calculus. All right? Which is
Are
what
we
we're
at
doing.
the high level of calculus?
Yeah, we are. Okay.
Please.
All righty.